brothers. So I'll just take a short session, 40 minutes, maybe till this first meeting ends. So no need to join back. So today we'll talk about case where we can obtain the probabilities using the standard form of the PMF and PDS. So we have understood the definition of probability mass function and probability density function. So probability mass function is just the set of probabilities observed for discrete values of x. Again, the probabilities observed for a range of x values, that is our density. Now, the statistical probability, the part of this concept produces a functional form of f of x. You can always obtain a functional form of f of x. And let's see how we can produce the functional form. So let me take this example of x is equal to number of heads when two coins are produced. So we have x taking values 0, 1, 2 because our sample space has 4 cases HH, HT, TH and TT. So when you count the number of heads, the possible values are 0, 1, 2, and we have already learned how to compute the probabilities also. I'm just stating it. In this case, the probability is this. Now, if you look into this, all these cases could be easily given by a function. So I can write this as, 2C0 half to the power of 0 half to the power of 2. 2C1 half to the power of 1 half to the power of 1. 2C2 half to the power of 2 half to the power of 0. So this 2C2 is actually telling you the number of ways. So these are just the combinations. You're familiar with this concept NCR, which is n factorial by n minus r factorial into r factorial. That is choosing r items out of n. So that could be done in NCR ways. Now, if I say when my x becomes 0, so x is equal to 0 indicates the happening of the event h comma h. Now, this h comma h can happen in only one way out of the 2 possible cases. So you're tossing the coins, 2 coins simultaneously. 2 coins, each coin will lead to one particular outcome only. So out of those 2 outcomes, you are expecting the same outcome, that is h comma h. So your h can happen in only one way, and mathematically 1 is equal to 2c0. Now, when you observe what is x is equal to 1, x is equal to 1 happens when your event is ht or th. So there are 2 cases. So that 2 is mathematically equal to 2c1. So you see 2c1 according to the definition 2 factorial by 1 factorial, 1 factorial, which is equal to 2. So this, the possible cases, possible ways of observing the various outcomes are generally given by NCR, where your R is the value taken by X and N is the total number of times you are tossing a coin. So not the sample space, not N is equal to 4. I'm talking about, if I say N is equal to 4, I mean I'm tossing 4 coins. So if I say what are the number of heads when you observe when you toss 4 coins, when you toss 4 coins, all 4 could be heads or all 4 could be tails. So your x takes value 0, 1, 2, 3, 4. And now you will have 4C0, 4C1, 4C2, 4C3, 4C4. And if you look into this form, half, it is also very easy to understand. We said that the distribution or the experiment is conducted under the assumption that the outcomes are equally likely. So there is a chance of half of observing head in the first coin, chance of half observing head in the second coin, chance of half observing head in the first coin, chance of half observing tail in the first coin. So when I say I am observing x is equal to 0 heads, 0 heads indicates 2 tails. So both 2 tails have the probability half half. So we are not observing tails, so it is half power 0. And we are observing, sorry, we are not observing heads, so it is 0. We are observing 2 tails, which is half into half. In the next case, when I say x is equal to 1, I mean 1 head. 1 head automatically indicates 1 head and 1 tail. So when and comes, you will have into, so half power 1, half power 1, and that can happen twice. So that's why you have 2c1, which is 2. Okay. So this is how. So okay, so the summary why I took this example is, whatever the probabilities you observe after writing the sample space, that probabilities in case of discrete or continuous case, we can come up with a mathematical formula. So we can come up with a mathematical law, and that law is what generally called as PML. So you can generalize this for any number of, say, n set of coins, and you're tossing them simultaneously for a large cases, and you can say x is equal to number of success or number of heads or number of tails. So generalization of this could be done, and those distributions which are obtained by using the functional form of f of x are called as standard distributions. So you can have both discrete distributions as well as continuous distributions. Now, in the field of statistics, there are several discrete distributions, like say uniform distribution, Bernoulli distribution, binomial distribution, Poisson distribution, then geometric, hypergeometric, many such cases are there. So we'll not, take each of these cases. We'll just look into some simple and commonly used cases. Those are Bernoulli, binomial, and Poisson. So when it comes to the field of medicine and the field of biostatistics, we'll look into what called as clinical trials. So you want to test a particular drug. So you will select some items randomly. You want to see what happens in this scenario if my probability that the drug will be reacted in an adverse, creating an adverse effect. Then if I inject this drug to so many cases, how many fatal cases will be there? So all those probabilities must be known to you as a researcher in prior, and in those cases, the most commonly used distributions are binomial and Poisson distribution. To understand binomial, you should have the concept of Bernoulli. So we'll start with Bernoulli. We'll see what happens to these cases. Now, these are all the discrete cases. So in each of these cases, you can say the particular specific values of x, like 0, 1, and so on. And most of the cases will deal with x equals 0, 1 only. We'll see why and how it comes. And then in case of continuous distribution, again, you have a case called as uniform. So we call this as discrete uniform. We call this as continuous uniform. Then you have exponential distribution. This is the most, widely used distribution when you look into the life of certain components. So life of bacteria, life of virus, life of electric components, etc. So in order to study that particular property, we'll use exponential distribution. And then you have normal distribution. Then you have beta distribution, gamma distribution, so many cases, but we'll just only stick to this distribution normal, because all distributions, whatever you study, under certain assumptions, they always tend to normal. Even your binomial, Poisson, your exponential, every case becomes normal distribution. So if you study normal distribution, you are studying all other distributions in the background. And the reason why it is called as normal is because whatever the variable of interest you take, whether it is, say, weight of a particular student, marks of a particular student, or number of defectives, number of defects in a large case, or even if you're talking about, say, growth of bacteria per minute, maybe per second, etc., any variable in nature, it always follows normal distribution. Of course, there are some theoretical conditions and practical conditions are there. So if those conditions are satisfied, then we can easily assume the distribution to be normal. Okay, so what we are doing here is, so till now, you obtain the probabilities either by writing the sample space or by creating a frequency distribution. So you conducted the experiment, like you throw the dice for around 100 times, 1000 times, then you observed how many cases are there, and you converted that into the proportion, the rate of frequency. That is what the probability in terms of statistical definition. So we have learned how to obtain probabilities using these two techniques. Now there are cases, things which are, bound to follow the natural laws. So some logic is there, and we are using that standard function. So standard distributions are nothing but now the probability distributions. So they are the probability distributions based on theoretical concepts. Until now, the probabilities what we discussed, they are almost like, say, based on the practical approach. So you are conducting the experiment, you are collecting the data, you are looking into possible cases of the experiment. Now here we are not talking about experiments. We are looking into the mathematical results, mathematical laws, mathematical theorems, which helps us in building the probabilities. So we use the mathematical functions, mathematical laws to generate probability. So we'll talk about first such case, Bernoulli distribution. I can use this distribution in the case where you're talking about Bernoulli experiment. There is an experiment called as Bernoulli experiment or Bernoulli trial. So this experiment is such that it leads to only two outcomes, two possible outcomes, which could be easily called as success and failure. Okay, so I said we are not using any practical approach, but understanding theoretical concepts are very easy when we have the practical approach. So we'll define Bernoulli distribution using mathematical function, but all mathematical concepts which are developed, they are developed for some practical applications only. So we have a practical case where I have some statistical experiment. The experiment is such that it is producing only two different outcomes, and those outcomes are classified as success and failure. Then such experiment is called as Bernoulli experiment. In all those Bernoulli experiments, you can use this Bernoulli distribution. That is, without actually looking into what is happening, you can come with the estimates of the probabilities. Now, what is this Bernoulli distribution? It has the probability function given in the form of p to the power of x into 1 minus p to the power of 1 minus x, where your x takes only two values, 0 and 1, and it is 0, p lies between 0 and 1. So if you are talking about a random variable which takes only two numbers, say 0 and 1, then the probability of observing these two different values are given by this model. So you need not look into sample space, you need not look into conduction of the experiment. Just if you know the value of p, you can obtain the probabilities. How can we obtain that? What is this p? So we'll see that. First we'll understand the distribution, then we'll talk about the practical approach. So your x in case of Bernoulli is defined as number of success in a single Bernoulli trial. So whenever you are taking a Bernoulli trial, either you will get a success or failure. Only two outcomes are possible. Now, count how many success did you encounter. So you are conducting a Bernoulli experiment and you are counting how many success you have got. So if your experiment is actually success, then you have got one success. If your experiment has failed, then you have got 0 success. So that's why when you count the number of success, you can have the possible values as 0 and 1. Next, coming to P. So this P is called as probability of success. And we know that probability always lies between 0 and 1. It takes values equal to 0 and 1. But in case of Bernoulli, we say it is strictly between 0 and 1. Why? The reason is if you take P exactly equal to 0, you will just get the probability as 1 here. If you again take P exactly equal to 1, again you will end up getting 0. So you'll get 0. The PMF is not at all defined. So that's why we say P should be a value within this. Now, how to generate the probabilities? You said this is probability mass function. So this is your PMF, probability mass function. So every time if you need some probabilities, put that value of X and generate it. How? You can easily do that. So that's why we say these are all standard distributions. So you said you have X is equal to 0 and 1. And you have P of X is equal to X, which is probability function, given as P power X into 1 minus P power 1 minus X. Now put X is equal to 0. So when you put X equals 0, you get P power 0, 1 minus P power 1 minus 0, which produces 1 minus P. When you put P X is equal to 1, you get P power 1, 1 minus P power 1 minus P. 1 minus 1 is 0. 1 minus P power 0 is 1, so just left with P. And if you look into the total probability, so you have 1 minus P plus P, which is equal to 1. Therefore, it is a PMF. So we call any probability density, probability distribution as a PMF if the total probability across all possible values of X is equal to this. But the question is still P. What is P? I said you have your past data, past experience. So that produces P. And for various P, you can have various Bernoulli distribution. So you can take any value of P. So let me say that I'm looking into a case where I have the sex ratio of a city. So let me say for every 1,000 males, there are 930 female babies. So this is what my past data is telling. So let me define success as observing a birth to a female child. Observing birth to a female child. So that is success. Or the other way to put this is you're counting number of success. The number of success can be defined as number of female babies in a single birth. In a single birth. So whenever a woman is giving birth to a baby, the birth could usually lead to a male baby or a female baby. So your giving birth can be taken as Bernoulli experiment because that birth is either producing a male baby or a female baby. Here I have defined my success as female baby. You can similarly model the Bernoulli model for a success where you are counting the number of male babies in a birth. Now, since we are talking about a single baby, Bernoulli is always based on a single trial. So, whenever a birth happens, you could observe a 0 female baby or 1 female baby. So, this is our X, which is number of success 0, 1. Now, what is P? So, we said P is probability that the new baby is female or the mother is giving birth to a female baby. So that is known from the past data. So you know the environment of that city, it always produces 930 females out of 1,000. So your P now is nothing but proportion of female births. Proportion of female births. And from the past data, we have that as 930 divided by 1,000 plus 930. So we are talking about proportion. So proportion of our female babies is nothing but total female babies divided by total birth. So it is not just 930 by 1,000, it is 0.4818. So even your practical cases produces almost equally likely. So just by simply taking what is the chance of observing the tail? So we said it is 50%, provided the coin is unbiased, but that is not, often what we observe in the practical cases. In the real life situation, giving birth to a female baby or giving birth to a male baby is not always same, but when you look into a large range, it is almost equal to this. So 0.48 is most closely to 0.5. So which suggests that probability of giving birth to a male baby is half, probability of giving birth to a female baby is half. That happens in most of the cases. But in certain states, certain cities, or certain geographical locations, the climatic conditions, the environment is such that it is favorable to either a male or a female. In such cases, you could have the values of P to be different. So always you can compute the values of P. Now, since I have the value of P, for this, the Bernoulli distribution becomes 0, 1 with probability. So we said we already derived for 0, it is 1 minus P, and 1 minus P becomes 0.5182. And it is P for x is equal to 1, which is 0.4818. And if you look into the total becomes 1. So this is the particular Bernoulli distribution for this case. So now in that locality, if you are observing a pregnant woman, and if you want to just have a guess what is the likely gender of the baby, you can say that it is most likely the male, because in that locality the probability of observing the male baby is higher than the female baby. But we rarely observe, application of this distribution when it comes to the concept of birth, because we have, the medical field is so advanced that even right at the time of the pregnancy, we can just look into what is the gender of the baby. So very rarely we come across the application of this distribution when it comes to the concept like this. Just to understand how the distribution works, I take this. Now coming to the usual application. So in the field of biology and medicine, we'll talk about P as a probability of success. And when you are looking into this, success is defined as the probability of curing or observing a probability of non-defective item in the production. So whether the drug is effective, probability that the disease is cured, or probability that the drug is effective. So in those cases, we have a lot of applications of Bernoulli. So you can have observing probability of defective. So you can call success as defective, and you say, I'm very happy if the number of defectives produced is very less. Or if you call it as probability of non-defective, then you will model such that the machine is set such that it produces a lot of non-defective items, and the proportion of that production will be very high compared to probability or the proportion of defective. So you have some past data. So often, when it comes to the clinical trials, you will observe the effectiveness of the drug. So you will give it for n patients or n items, or which we call basically as n units, experimental units. You will inject the drug and you'll see how many got cured, and this ratio is taken as our probability. Number cured, the total patients whom the drug is administered. So this is how the clinical trial works. So basically they start with 1%, then take 2%, then they take 10%, 100%, 1000%, and even in some cases, if possible, they go up to 10,000 and 1 lakh trials also. Only then if they see that they are getting, the probability is to be very high, then the drug will be, let into the market. So this is what happened even in case of corona. Though they say that they are investigating, they are success in producing the drugs, before happening the clinical trials, that will not come to the market. Now the question is, who are willing to, take chance with their life? There are people, very poor people, people who are willing to take up those trials. So if success, they'll be paid with a large amount of funds, money. So we'll not talk about that. So we have a case where P could be called as probability of success. So you have enough data with you, or you can do some experiments and obtain the value of P. So that is about Bernoulli trial. Now, if you look into the mean and variance of Bernoulli distribution, so in the last class, we came up with a formula to find the values of mean as well as variance. And if you apply the same formula for the Bernoulli distribution, where you have x is equal to 0, 1, the probabilities are 1 minus p and p. So you have x and px, mean is equal to sigma x px, variance is equal to sigma x square px minus sigma x px whole square. So compute x px, x square px, obtain the mean. We will observe that the mean comes to be equal to p and variance comes to be equal to p into 1 minus. So that this is not a pure statistical, course. We are just looking into concepts of statistics, how it is applied. So we'll not look into derivations of any sort. We'll just observe the statements. So these are the mean and variance for a Bernoulli distribution. Now, in case of Bernoulli, we said x is equal to number of success in a single trial, and that trial is called as Bernoulli trial. Now, what we do is we can define so many such trials, x1, x2, x3, etc., xn, where all are counting the number of success in a single trial, Bernoulli trial. So you can take a Bernoulli trial as say tossing a coin. So tossing a coin is a Bernoulli because coin leads to only two possible outcomes, head and tail. You can take your head as success or tail as success. Every time you're counting number of success, so you could observe number of heads to be 0, 1 or number of tails to be 0, 1 whenever we take the experiment. Therefore, all are Bernoulli cases. So you take the coin, you toss it once, whatever the outcome you observe, you call it as x1. You take the coin, you toss it the second time, whatever the observe you call, that is again the Bernoulli with x2. So similarly, if you talk about n coins, now the model is same as your say tossing coin 1, tossing coin 2. Now the other way to put this mathematically, you are tossing n coins together. And if you look into the outcomes are not dependent. You could say outcomes are independent. Why outcomes are independent? Because there is no rule which tells that if you observe a head in this case, in the second toss you will definitely observe head. So there is no such rule. So there is no dependency in the results of the successive trials. So we say outcomes are independent. So if you are talking about repetition of Bernoulli experiment, and if each experiment is independent, and in all the cases P is same. Now since we are tossing the same coin, probability of success is same. Or maybe if you are talking about a different coin also, we'll take the coin such that the value of P is same. So you can take n or 6 1 rupee coins, 6 2 rupee coins. So the coin structure is same. So we assume the value of P is same. In that case, you can talk about sum of Bernoulli. Sum of Bernoulli. So here simply mathematically it is just x1 plus x2 plus etc. up to xn. But when you look into the practical cases, so it is you have tossed coin 1, coin 2, coin 3 and coin n. Now we are looking into the total outcomes. So in this case it was number of success. Now your sum is total number of success. So if you observe this to be say success as number of heads, so how many heads in the first coin, how many heads in the second coin and so on, how many heads in the seventh coin, or you can just say what is the total number of heads in all those 7 coins. So if you are tossing 7 coins, you likely observe the number of heads to be 0 or 1, 2, 3, 4, 5, 6 up to 7. So you have your x1 plus x2 plus xn taking the values 0, 1, 2, etc. up to n. Okay. But we have already understood this model. So we looked into the sample space of tossing 2 coins, 3 coins, 4 coins, and we saw how the number of heads becomes 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, respectively for 2 coins, 3 coins, or 4 coins. This is the background, mathematical work happening behind those cases. So this x1 plus x2 plus xn is also a variable because it is taking different values. Any characteristic which can be quantified, which takes different values, that is called as a variable. So this is the variable with respect to the random experiment of tossing n coins or several coins n times. Therefore, this becomes a distribution, and that distribution is called as binomial distribution. That distribution is called as binomial distribution. So we have a functional form of this binomial. Also, in case of Bernoulli, we just called it as p power x, 1 minus p power 1 minus x. But in case of binomial, it is ncx, p to the power of x, 1 minus p to the power of n minus x. With now x taking the value 0, 1 to n, and p again between 0 and 1. So this entire distribution depends on what is the value of n and what is the value of the Bernoulli p. So we say n and p are parameters. In case of Bernoulli, just p is the parameter. So you should somehow obtain the value of p. If you have observed p, the entire distribution properties are known. Here you should know what is n, you should know what is p. So we define simply n as total Bernoulli trials. Total Bernoulli trials, and P is probability of success of a single Bernoulli trial. So to understand binomial, we need the Bernoulli case. Okay, so what is this telling? So here it is simply that you're talking x number of success out of n. Let's say you're tossing n coins and you're counting how many total successes are there. Now, since you're counting out of n, naturally your x can take values 0, 1 up to n. So this is the binomial model. Now, if you want to ask the question, what is the probability of observing 2 heads when 2 coins are tossed? So we know this answer already because the last class we have observed that whenever we toss 2 coins, the possible values for number of heads is x is equal to 0, 1, 2, and we know the elements in the sample space, which is HH, HTT, HTT, and because of which we have the probabilities 1 by 4, 2 by 4, and 1 by 4. What is the probability of observing 2 heads when 2 coins are tossed? The answer is 1 by 4. So here, first I should know what is the value of P, what is probability of success of a single Bernoulli trial. So if I'm talking about this situation, then when a coin is tossed, probability of observing head is half, probability of observing tail is half. So the events are equally likely. That's why we are observing these probabilities. So I know what is probability of success for a single Bernoulli trial, so which is taken as P. And now I'm tossing 2 coins. So I have a case where n is equal to 2, p is equal to half. So when I put this n is equal to 2, p is equal to half here, and I need the case where I'm observing 2 heads. That means I'm observing exactly 2 success. And we define x as number of success. X takes value 0, 1 to n. So if I need probability for 2 success, that is same as p of x is equal to 2. When you have n equals to p equals half. So when you substitute that, you get 2c2, which is ncx, then p power x half power 2 into 1 minus p, which is 1 minus half, to the power of n minus x, which is 2 minus 2. Mathematically, 2c2 is 1, so we get half square. 1 minus half is half. Half power 2 minus 2 is 0. Half square is 1 by 4. That is what we have observed. But why do we need this when we can simply obtain the probabilities? The answer to that question is your P is not always equal to half. It is any probability which is between 0 and 1. You could have the coins, bias coins, where it produces 60 times heads compared to number of tails. So P times we are observing heads, 1 minus P times we are observing tails. In that case, we need this model. So you can have a case where your P is actually equal to 0.25. Now your coin is such that it produces only heads 25% of times. In that case, if I ask you this, it becomes very difficult because your hedge is such that now hedge happens 25% of times. Tail happens 75% of times. So it is no more 1 4 2 4 1 4. It will be the product of these two now. So every time your n changes, it happens, and we can actually tabulate those cases even in this case for a different P. But we have only two cases, 2 coins, 3 coins, 4 coins. But when you talk about 5 coins, 6 coins, and so on, your n of s will be 2 power 6. So we know this. If you repeat a experiment with 2 outcomes 6 times, the total possibilities will be 2 power 6. So it becomes difficult to look into the sample space, number of elements in the sample space to compute probability. So we use this distribution called as binomial. So I'll end the session here today. So we have learned the binomial distribution. We'll look into the problems. So NNPR parameters. So in this case, mean is equal to NP and variance is equal to NPQ. So memorize these two. Bernoulli PMF, Bernoulli mean, variance of Bernoulli, binomial PMF, mean of binomial, and variance of binomial. Okay. So Saturday we'll have practical class. So Saturday the class will be at 8.